So if I had to give you chapter 7, Similarity, kind of at a glance, what are the highlights of this chapter? It's all about similar figures. And in order for two figures to be similar, they have to have the same angles. So for instance, if I had a triangle that had 30 degrees and 100 degrees, that would be 130. So this one would have to be 50 degrees. This is obviously not drawn to scale. And I had another triangle that looked like this, and this was 30 degrees, and this was 100 degrees, and this was 50 degrees. Let me see if you can see this. Here, over here. This was 50 degrees. Then these two triangles would be similar as long as the ratio of this side to this side, this side to this side, and this side to this side were the same. So let me redraw this so that it's a little bit easier for me to work with. So if I have one triangle, this was 30 degrees, we'll say this was 100 degrees, and this is 50 degrees. And then if I have another triangle where this is 30 degrees, this is 100 degrees, and this is 50 degrees, then I can take a look at the side. So if I said, if this side was 3, and this side was 15, and this side length was 2, and this was 10, and this side length was 5, and this side length was 25. Now I could write a ratio of the sides. Now when I write a ratio of the sides, they have to be corresponding sides. I can't write a ratio of this side to this side, right? It has to be the same side. So this side is between the 30 and the 100 degree angle. So I have to set it a ratio with the side that's also between the 30 and the 100 degree angle. So if I write a ratio of the sides, I would have 3 over 15, this side to this side, then 2 over 10, and then 5 over 25. So that's a ratio of their sides. Now, if I simplify each one of these ratios, if they all equal each other, then these two triangles would be similar. If they do not equal each other, then these two triangles are not similar. Well, I can divide both of these by 3, so this would be 1 over 5. I can divide both of these by 2, so this would be 1 over 5. And I can divide both of these by 5, so this would be 1 over 5. So therefore, you know that each one of those ratios are congruent, so therefore these two triangles are similar. So in order for them to be similar, they have to meet two criteria. The first criteria is all the angles must be congruent, so all angles must be congruent. And then the second criteria is that the sides have to be proportional. And if it meets those, here you go, proportional. If it meets those two criteria, then the figures are similar. And this would be true for any figure, triangles, squares, rectangles, whatever you have. All right. Then there's this thing called the side splitter theorem. And the side splitter theorem says that if you have a figure and these two lines are parallel, so this is parallel to this side, then it'll break these sides up, like if I called that A, B, C, D, it would break these sides up so that they are proportional. So therefore, I could write a ratio that A is to B, this side is to this side, as D is to C. Now, if you start with A and go up, you have to start with D and go up. I could do it the other way. I could say B is to A as C is to D. B is to A as C is to D. As long as I start at the bottom in the first ratio, I'd have to start at the bottom on the second ratio. So let's see how we would use this. So if I have some triangle like this, and I'm telling you that these sides here are parallel, and I'm going to say this is X and this is 8, and I'm going to say that this is, I don't know, 5, and this is 10, for instance. Now I can write a ratio that will help me solve this particular figure for x. Because these are parallel, I know x over 8 has to equal 5 over 10. So let's write that ratio. X over 8 has to equal 5 over 10. Well, now I have a ratio. In order to solve this ratio, I need to cross multiply. The way you cross multiply is you take these two terms and multiply them together. So x times 10 will give me 10x. And then you're going to take these two, the other two, and set this product equal to the product of those other two. So 8 times 5 is 40. So now I have cross multiplied. Now in order to solve this, I just have to divide both sides by 10. And now I've solved for x. I know that x has to be 4. And now the other thing is true as well. If I didn't know that those were parallel, and I knew that this was 4, I could prove that these two lines are parallel by saying that these ratios are the same. So I could say 4 over 8 is 5 over 10. If I simplified that, that would be 1/2 equals 1/2. Since those ratios are the same, therefore I know these two have to be parallel. So a theorem works both ways, kind of going forwards and going backwards, if you will. And then there's one more theorem called the mid-segment theorem, which will tell you if you have some sort of a triangle and it's cut in the middle. So it has to be cut in the middle. So this has to be congruent to this, and this has to be congruent to this. These two don't have to be the same, but going up and down the sides, they have to be the same. This has to be the middle of whatever figure you're drawing. In this case, it's the mid-segment theorem of a triangle, so it would be a triangle. In that case, this shorter segment here is always going to be half of the bigger segment. So if this was 5, this would be 10. If this was 2, this would be 4. If this was 8, this one would be 16. Now you can go the other way as well. If I know the longer side, if I knew this side was 10, I know the shorter one would be 5. It would have to be half of it. If this one was 18, I know this one would be 9, and so on and so forth. But please remember, this is only true if these two are congruent and these two are congruent. And then the last thing that they talk about in this chapter is called a dilation. And a dilation is nothing more than making a figure bigger or smaller. So therefore, they would be similar. So all similarities, if you have two similar figures, they could be a dilation. Now, a dilation could be an enlargement. Whoops, I spelled that wrong, sorry. A dilation could be an enlargement, which means it would be getting bigger, or it could be a reduction, which means it's going to get smaller. And whenever you have a dilation, you could figure out the scale factor. And the scale factor tells you by how much is something getting bigger or smaller. And the way you figure out the scale factor is you always take the scaled figure and create a ratio with the original figure. So it's always scaled over the original. Okay? So let's take a look at an example. Now, when you're drawing a dilation, the first figure you draw, for instance, if I do a triangle, I would call this ABC. And the scaled factor, I would call A prime, and it's showed by a little like that, B prime, and C prime. So by doing this, you always know which is the figure you started with. So in this case, I started with this figure, and I'm scaling it to this figure. So if the scale factor is greater than 1, like in this case, and I'll show you that in a minute, if it's greater than 1, then this would be an enlargement. which means that my triangle is getting bigger. And if my scale factor is less than 1, that means it would be a reduction, which means my figure would be getting smaller. So if this one here was A, B, C, and this one was A prime, B prime, C prime, it would be getting smaller, so it would be a reduction. So let's take a look at an example here. If I had two figures, let's say I started with this one here, A, B, C, and I went to this one here, A prime, B prime, C prime. Well, you know that this is a reduction because it's getting smaller, it's not getting bigger. And I can do a couple of ways to figure out the scale factor. One way would be if I took corresponding sides. So let's say this was 8 and this was, I don't know, 6. Okay. I can figure out what the scale factor is. So remember, scale factor, you always are going to put the new over the original, or the scaled factor over the original. Well, this is the new one. This is the scaled one. So I would put 6 over the original, which is 8. If I reduce that fraction, I can divide both by 2. This would be 3/4. So what this tells you is this new triangle is 3/4 the size of this triangle. By doing your scale factor as new over original, you'll always get the right scale factor. So you can see this is less than 1, which tells you that this is a reduction. If I went the other way, if I started with a larger figure, A, B, C, I'm sorry, if I started with a small figure, A, B, C, and I went to a larger figure, A prime, B prime, C prime, I could figure out its scale factor by putting new over original. Now, another way you can do this is sometimes they'll draw like little dotted lines from B to B prime and from C to C prime and from A to A prime, and they'll give you the lengths of those figures. So, for instance, if they said this length was 10 and this length was 20, then I could also figure out what the scale factor is by putting my new over my original. So I know this is getting bigger, so I'll put 20 over 10, and I can reduce that to 2, so I know that this is getting bigger because it's 2. All right? Or another way, if you didn't do that, if you just had your sides, you could do your corresponding sides, right? A, B, C, A prime, B prime, C prime. If I knew that this was, I don't know, we'll say this is 15 and this was 3. If I wanted to figure out my scale factor, I'd take my new one, which would be 15, and put it over my original, which is 3. So I know my scale factor is 5:1, which would tell you that this is 5 times bigger than this one. All right, if you have any questions, let me know.